I am Ennemcien. I have introduced radioactivity and the law of disintegration and derived the decay formula n equals n0 e to the power of minus lambda t. Now we have to see some basics before going further. First is the units of radioactivity. One unit is becquerel. When you write the full name, you should start with the small letter. That is an international convention. So one becquerel, short form capital B small q, becquerel, means one disintegration per second. One atom disintegrates every second. Then the activity or dN by dt is 1 becquerel. Unit of radioactivity means unit of activity, that is unit of dN by dt. Number of atoms disintegrated per second, that is expressed by these units. Next unit is Curie. See, the starting letter is written in small letters, as small letter C, capital C, I. 1 Curie means 3.7 into 10 raised to 10 disintegrations per second. Next unit is Rutherford, RD. It is 10 raised to 6 disintegrations per second. These are the three units usually used to express activity. The next point is, these are silly things, isotopes. Isotopes are atoms of same element having same atomic number but different mass numbers. You are familiar with isotopes of hydrogen, 1H1 protium, 1H2 deuterium, 1H3 tritium. Then isotopes of oxygen, 8O16, 8O17, etc. You know a number of isotopes. Then we see isobars, the reverse. Same mass number, and these are atoms of different elements having same mass number but different atomic number. See, isobars, nitrogen and oxygen having mass number 17, same mass number but atomic number 7 and 8. Argon and calcium, 18, 40, 20, 40. You can see also, other examples from your data book. Next point is isotones. Isotones are atoms of different elements having same number of neutrons. Now, a nucleus is composed of protons and neutrons. These two particles are combined known as nucleons. Total number of nucleons, that is total number of neutrons and protons, is represented by the letter capital A, called mass number. Total number of protons is called atomic number, represented by the symbol Z. The number of neutrons is A minus Z. This must be same in the case of isotones. So, these two elements, AR and K, atomic number 18, mass number 39. So difference number of neutrons is 39 minus 18. K, mass number is 40, atomic number is 19. Difference is the same number of neutrons and so on. Next point is mass defect. You know that when a system is formed, I have said it earlier, stability is an important factor. Energy must be minimized when a system is formed. That is the law of nature. A nucleus is formed by combination of a number of neutrons and protons. When they come together and form the nucleus, energy must be minimum. So the system will release a, a certain amount of energy to achieve stability. This energy is obtained from the mass of the constituent particles. That is, suppose 8 protons and 9 neutrons combine to form a nucleus. Then the total number of the nucleus is found to be less than the total number of protons and 8 protons and 9 neutrons before combination. This difference in mass, that is total number of nucleons before forming the nucleus minus total mass of the nucleus, is known as mass defect. Mass defect is given by delta M equals Z into MB. Z is the number of protons or atomic number into MB is mass of a single proton plus A minus Z is the number of neutrons into Mn, mass of a single neutron. So this is the total number of the nucleons before forming the nucleus. This minus M. M is the total mass of the nucleus. So this is the mass defect of the nucleus. The energy equivalent of this mass defect is called binding energy of the nucleus. This is determined using Einstein's mass energy relation E equals mc square. So binding energy of the nucleus is delta M into c square. E equals binding energy equals delta M mass defect into c square, where c is the velocity of light in free space. Another quantity is packing fraction. Packing fraction is the ratio of mass defect to the mass number. That is, packing fraction is delta M by A. Another point is binding fraction. Binding fraction is the ratio of binding energy to the mass number. Binding energy by mass number. Now, a unit of mass is defined in atomic and nuclear physics because these particles are too light to be expressed in kilogram and gram like that. You don't weigh the mass of an ant in ton or kilogram. You can use the units ton, kilogram, etc. to represent the mass of an elephant. But you can't use the same unit to express the mass of an ant. Similar to that, atomic particles are extremely light, so a separate unit is defined, and that is called the atomic mass unit. Symbol is U. One atomic mass unit or 1 unit is 1.66 into 10 to the power of minus 27 kilogram. This is extremely small. So just you convert atomic mass unit into kilogram, just you multiply by this factor. So mass of helium is 4 units, means that is 4 atomic mass units. If you want to express it in kilogram, you should multiply 4 by this factor. 4 into 1.66 into 10 to the power of minus 27. Now, energy equivalent, if this one mass unit is converted into energy, that is energy equivalent, is given by 931.2 million electron volts, where 1 electron volt is 1.6 into 10 to the power of minus 19 joule. I have told you this earlier. Now, next point is binding energy curve and stability of nucleus. You know that every system likes to be stable. Stability is the ultimate aim of every process. So when a nucleus is formed, it should be stable. If a nucleus is not stable, it will disintegrate to become stable. That is radioactivity. Now, a graph is popular. Mass number is plotted on the horizontal axis and binding energy fraction on the vertical axis. High binding energy means more stable, because you will require large amount of energy to separate the nucleons, to disintegrate the nucleus. So large binding energy means high stability, and low binding energy means low stability. Now the graph is like this. There is a peak, and this peak means high binding energy of the order of 8 million electron volt per nucleon, because this is binding energy by mass number. The peak values occur in between the mass numbers 50 and 60. So elements or atoms in this range are more stable. Light elements and heavy elements are less stable. More than 1,400 isotopes are known till today. Out of these, only about 20 or 25 atoms are stable. All other isotopes are unstable. So what is the implication of this particular shape? Light atoms, in order to acquire stability, will try to become more massive to come into this range. That is, light atoms will show a tendency to fuse together to acquire more stability, that is, to fall into this range. That is why fusion is possible. Understand? Then, heavy elements beyond 60 are heavy elements. These elements are not stable because binding energy is less. What will they do? They will try to reduce their mass by splitting up, that is, by fission. So heavy nuclei show tendency to split apart or to make fission process to achieve stability by coming into this range. So this is the implication of this graph. So fusion and fission, these two processes are the law of nature by which stability is achieved. Thank you.